Welcome to Lecture 56, the first of two lectures on nuclear physics. In this one, we'll take a look at basic nuclear physics, and in the next lecture, we'll try to understand how we get energy out of the nucleus. Now, nuclear physics, more perhaps than any other area of physics, is deeply entwined with history, with international politics, and indeed with the fate of the world. There are still thousands of nuclear weapons enabled by our knowledge of nuclear physics, and they pose a threat to the very existence of human civilization. So whenever I'm thinking about nuclear physics, that threat is not far from my mind, along with other worrisome aspects of nuclear physics, for example, nuclear reactor accidents. So let's plunge right into the nucleus, and let's look first at how it was discovered. So the discovery of the nucleus begins in about 1896 with Henri Becquerel discovering, quite inadvertently, the phenomenon of radioactivity. He had some photographic film in a drawer, and the drawer was containing uranium compounds, uranium salts, and he found that these uranium salts fogged the photographic film. J.J. Thomson in 1897 discovers the electron, recognizing that atoms are not indivisible, and out of Thomson's discovery comes what's called the plum pudding model of the atom, in which the atom consists of a sort of pudding of positive charge with individual electrons within it. Marie and Pierre Curie discovered the radioactive elements radium and polonium, polonium named after Poland, Marie Curie's homeland, and Marie Curie was the first to coin the term radioactivity to describe these elements. And the significance of the Curie's discovery is that the high-energy particles coming out of these radioactive materials gave us tools to probe the nature of the nucleus. And Rutherford, Marsden, and Geiger, Marsden was an undergraduate, by the way, Geiger of Geiger counter fame, did a series of experiments in 1909 to 1911 in which they bombarded a thin foil with some of these high-energy particles from radioactive radium. And by seeing how the particles recoiled, they were able to conclude that the atom consisted of a very tiny massive center, the nucleus, surrounded by mostly empty space in which the electrons were orbiting. And from that came the classic solar system model of the atom. And we've already seen in studying quantum physics that this model is not quite correct, but it certainly still is correct to think of the nucleus as a tiny but very massive particle at the center of the atom. And the last step in this discovery is Chadwick's discovery of the neutron in 1932, and at that point we came to understand that the nucleus consists of protons and neutrons. I'm going to represent neutrons in gray and protons in red, and so here, for example, is a helium nucleus. Now, what does it mean to be an atom of a particular element? Well, when we have a nucleus, the nucleus is positive, and the nucleus attracts electrons, and in a neutral atom, the number of electrons equals the number of protons. But it's the electrons that determine an atom's chemical properties. Remember that it's those outermost electrons that participate in the chemical bonding that makes atoms join into molecules and so on. So the number of electrons determines the chemical properties, but the number of electrons is determined by the number of protons. So the number of protons in the nucleus determines the chemical properties of a particular atom. We call that number of protons the atomic number, and we give it the symbol Z. There's another use for A, so don't get confused. Z is the atomic number. It's the number of protons. And all atoms with the same atomic number belong to the same chemical species because they have the same number of protons in their nucleus, and therefore they have the same number of electrons surrounding them, and therefore they have the same chemistry. They are atoms of the same chemical element. So that's what makes an element. You tell me atomic number Z equals 2, and I know I've got helium. Helium is synonymous with Z equals 2. Carbon is synonymous with Z equals 6. Those things mean the same thing. However, the number of neutrons in a nucleus is not determined by anything chemical. It doesn't matter chemically. You could add or take away a neutron and you'd still have the same number of protons, the same number of electrons, and the same chemistry. And so it's possible to have atoms of the same element which have different numbers of neutrons, and we call those different isotopes of the same element. They have different numbers of neutrons. They have the same atomic number Z, so they're chemically similar. They're not absolutely identical because they have slightly different masses, and that makes them behave slightly differently in ways that are interesting, but not really significant for our purposes here. They have different mass numbers, however, and the mass number, which we designate by A, is the total number of nucleons, where a nucleon means either a proton or a neutron. So you add up all the protons and neutrons, and you get the mass number. And the mass number, by the way, is approximately, but not exactly, the mass of the nucleus. It's not exactly the mass of the nucleus in atomic mass units because of the energy that is involved in binding the nucleus together, and the E equals mc squared energy changes associated with that mass. So the mass number provides a rough indication, but not an exact indication, of the mass of a nucleus. So here, for example, is helium-4, the most common kind of helium, 2 protons, 2 neutrons. Here's helium-3. It's still helium because it's got 2 protons, but it's only got 1 neutron. It's actually a very rare isotope of helium, very important in some low-energy physics studies. These two behave similarly chemically. That is, helium is an inert gas. It doesn't participate in chemical reactions, but they behave quite different physically because of their different masses and because one's a boson and one's a fermion. So we give them the symbol 4He2 or 2He4. Read it from the bottom, 2He3, where a nuclear symbol looks something like this. Here's the anatomy of a nuclear symbol. The element symbol is typically a 1 or 2 letter combination. Here it's 3 letters SYM for symbol. The atomic number appears as a subscript before it, and the mass number appears as a superscript above it, before it also. So there's an atomic symbol, and I will be using atomic symbols like this throughout, nuclear symbols. Some other isotopes, again, protons in red, neutrons in gray. Hydrogen, the most simplest element, just a proton. But there's also deuterium, a heavier isotope of hydrogen, a stable isotope which comprises about 1 in 6,500 hydrogens. And then there is an unstable isotope, one that's radioactive, called tritium. You'll hear about tritium whenever a nuclear accident happens. Tritium is commonly released. So those are 3 isotopes of hydrogen. Oxygen has actually 3 stable isotopes. Oxygen 16, 8 protons, 8 neutrons is by far the most common, but oxygen 18, there's a little bit of that, which has 2 more neutrons, 10 neutrons and 8 protons. And the isotopes of uranium are particularly important to us. Uranium-235 has 92 protons and 143 neutrons, and uranium-238 has 92 protons, that's what makes it uranium, and 146 neutrons. And although those behave very similar chemically and have almost the same mass, they are very different in their nuclear properties, and uranium-235 comprises only 0.7% of natural uranium, which is actually a very good thing for the world for reasons we'll get into later. How do we make nuclei out of neutrons and protons? Well, there are 2 forces involved in building a nucleus. There's an electric force that we've already encountered that acts repulsively between protons, and it tends to tear the nucleus apart. The electric force is weak, but it extends over fairly long distances. As we know from our study of electricity, it falls off like 1 over r squared. Then there's a nuclear force, and the nuclear force acts attractively between all the nucleons. It acts between protons and protons, protons and neutrons, neutrons and neutrons. As you'll see in lecture 58, it's actually a kind of residual effect of a strong force that binds the quarks together to make protons and neutrons. So the nuclear force is very strong, but it's also very short range. It falls off approximately exponentially. And the consequence of this is that larger nuclei need more neutrons than they have protons. Here's why. Here's a picture of a large nucleus. There's a proton and a neutron being bound together by the nuclear force. There's a couple neutrons being bound together. There's a couple of protons being bound together by the nuclear force. But there are 2 widely spaced protons that are being pushed apart by the relatively long-range electric force, but they don't have any compensating nuclear attraction. And so to compensate for that repulsion of distant protons in a big nucleus, the nucleus has to have more neutrons to comprise a kind of nuclear glue that holds the whole thing together. And if you were to plot on a graph, on the horizontal axis here, the number of neutrons, n, the mass number minus the number of protons, so n is a minus z, versus the number of protons on the vertical axis, you would find that smaller nuclei, lighter nuclei, tend to have equal numbers of protons and neutrons. Normal carbon, carbon-12, has 6 protons and 6 neutrons. Normal oxygen, oxygen-16, has 8 protons and 8 neutrons. Normal helium has 2 protons and 2 neutrons. And that's reflected in this graph by the line going up essentially diagonally. All the little dots on this graph are known nuclei. And pay attention particularly to the black dots. Those are nuclei that are stable, that can exist forever without flying apart by radioactive decay. But as we get up in numbers of nucleons, you see that curve bending over a bit. That curve is bending over because there become more neutrons than protons. So more massive nuclei tend to have more neutrons than protons in order for them to be stable. By the way, this curve, as we'll see in the next lecture, has a lot to do with why there was so much worry after the Fukushima nuclear accident in Japan about the overheating of nuclear fuel, even though the reactors had shut down during the earthquake that was the original cause of that accident. So this is the chart of the nuclide. It shows all the existing nuclei. There aren't any nuclei way up to the upper left because they would have too many protons. They would be unstable because the electric force would drive them apart. There are also no stable nuclei down in this lower right region because they would have too many neutrons. And it turns out that the neutron itself is an unstable particle, as you'll see, and it would decay. And contained within a nucleus, a stable nucleus, it doesn't decay, but otherwise it would, or if there are too many neutrons, it will decay. And so instability also results down there. So this fairly narrow band contains the stable isotopes and some of the other isotopes that aren't stable but last long enough for us to measure them and understand them and know their properties. That's the chart of the nuclides. What happens to nuclei that are not stable? Well, eventually, and later in this lecture I'll clarify exactly what I mean by eventually, they decay. That is, they spew out some particles and turn into something else. One mode of decay, the mode favored by proton-rich nuclei, the ones that have too many protons, is to emit what's called an alpha particle. And an alpha particle is just the name for a helium-4 nucleus. When I say helium-4, I mean the version of helium with 4 nucleons total, mass number 4. Helium-3 would be the version with 3 nucleons. And here's the reaction written for the decay of uranium-238, the most common kind of uranium. It starts with uranium-238, goes to thorium-234, and spews out an alpha particle. Let's take a little closer look at that reaction before we look at other radioactive decays. So here's an anatomy of a nuclear reaction. Uranium-238, 92 protons, 238 total nucleons, decays to 234, thorium-234, and helium-4. The original nucleus is on our left. The first nucleus on the right is called the daughter nucleus, and then out comes what's really nuclear radiation, a high-energy particle. So that's the anatomy of a nuclear reaction. And if we want to make sure we've got it right, we check the numbers. We had 238 mass numbers on the left. We have 234 plus 4 on the right. Yep, 238. We've got 92 protons worth of electric charge is basically what we're looking at here. And on the right, we've got 90 plus 2, 92. So that's good. So let's go on and look at the rest of the nuclear reactions that we'll be considering, radioactive decays here. We've got alpha decay. Here's beta decay. Beta decay takes place in nuclei that typically have too many neutrons. The neutron decays to a proton, an electron, and one of these elusive particles that's chargeless and almost massless called a neutrino. It's called beta decay because the high-energy electron that comes out is a beta particle. It's called a beta particle. So here on the left I have carbon-14. This happens to be the reaction used in radiocarbon dating. We'll get to that a little bit later. Decays into normal nitrogen, nitrogen-14, an electron with atomic number -1 because it has one negative charge. It's so light it has no mass number. And out comes the neutrino, also that nu, which is in fact actually an antineutrino. There's another kind of beta decay in which a proton becomes a neutron and emits a positron and a neutrino. And that takes the atomic number down 1 instead of up 1, as with ordinary beta decay. Here's the decay of oxygen-15, a radioactive isotope that's used in PET scanning, positron emission tomography. Gamma decay occurs when a nucleus gets excited in a way analogous to the way an atom can get excited by its electrons rising to higher energy levels. The excited nucleus drops to a lower energy level, emitting a high-energy photon, also called a gamma ray. The nucleus itself hasn't changed. All it's done is shed some energy. So it's written on the left with a star to show it's excited, and on the right without the star. And this is the decay of technetium-99, which is widely used in medical radioisotope imaging, for example. So that's radioactive decay. So where do we get these radioactive isotopes? Some of them we make by nuclear reactions in particle accelerators and nuclear reactors, but others exist in nature. How do they exist in nature if they're radioactive and decay away? Well, here's an example. This is the decay series of uranium, uranium-238. It starts out and it decays by the first reaction I showed you, by an alpha decay to thorium-234. Then it undergoes a sequence of beta and alpha decays that produce a whole host of other radioactive elements. Among them is radium-226, which was the isotope Marie Curie discovered. Among them also is radon-222, which is a very short-lived radioactive gas which seeps into your basement from the decay of natural uranium in rocks and concrete and can build up significant levels of radiation in basements. This sequence goes on until it finally ends with a stable isotope, which is lead-206, and lead-206 is formed ultimately from uranium. So there's a decay series for uranium. To see that we understand these radioactive decays, let's take a look at another decay series on our big screen monitor here. Here's the decay of thorium-232, atomic number 90, mass number 232, symbol TH. It begins with one alpha decay. It's followed by two beta decays, then a bunch more decays. But my question is, what's the daughter nucleus at the end of these first three decays? Now, we know about alpha decay that it sends out an alpha particle, a helium-4 nucleus, so that reduces the mass number by 4, and the helium nucleus has 2 protons, so that reduces the atomic number, equivalently the electric charge, by 2. So A is going down to A minus 4, Z is going to Z minus 2. So the first reaction looks like this. We start with thorium-232, we go down to some daughter nucleus, I'll just call it D1. I'm not even being asked about it. It has atomic number 88 and mass number 228, and it spews out that helium nucleus, 2He4. Then there's a beta decay. The beta decay keeps the mass number the same because it sends out an electron, and an electron is so light it essentially has almost no mass for these accounting purposes. But it does raise the atomic number, raises the electric charge by 1 because it sent out a negative charge. So those are the changes from the beta decay. So now we've got daughter 1, 88, 228, whatever it is, goes to same mass number, 228, but up 1 atomic number, 89. That's daughter 2, and out comes the electron and also the antineutrino. The next reaction is also a beta decay. So daughter 2, 89, 228, daughter 2 goes to 90, up 1 again, 228. That's daughter 3. That's the one we're being asked about. And the electron comes out and the antineutrino. And you'll notice we have 90 for daughter 3. We started out with thorium-90. That's what makes it thorium, the number of protons in the nucleus, the atomic number. So this is thorium-228. So that's our answer, thorium-228. So the thorium is decayed through 3 decays and been thorium again. If you want to know what the others are, you just look at a chunk of the periodic table and you can see that daughter 1 is radium, radium-228, and daughter 2 is actinium-228. Those are both here on the periodic table. So that was a decay series. Now, I've been beating around the bush with this question of how rapidly do these radioactive materials decay? And the answer is there is a certain time in which roughly half the nuclei in a given sample will decay. That's called the half-life. I can't give you anything more precise than that because it's a kind of a statistical thing. But if I start with 1,000 nuclei, after one half-life, I might have 495 or 503 or something like that, but I'll have something on the average of about 500. And the more I have, the more accurate that becomes. These half-lives range from fractions of a second to billions of years, and the number of nuclei after a given time is described by the number n sub 0 you started with times 2 raised to the power minus t over the half-life. Minus t is the time. Number of nuclei at time t, initial number of nuclei, and the half-life. And if we plotted a graph with time on the horizontal axis in half-lives and number of nuclei, and we start with 100%, 1, I'm just calling it. After one half-life, we're down to half as many as we had. After 2 half-lives, we're down to a quarter as many. After 3, an eighth as many, and so on. Just to give you some examples of elements that have interesting half-lives and are isotopes that are interesting to us. Uranium-238, the naturally occurring most dominant isotope of uranium, has a half-life of 4.5 billion years. That's why it's been around since the Earth's existence. It's the dominant isotope in natural uranium. Uranium-235, the one that we use to make nuclear power, the fissile isotope in weapons and reactors, that has a half-life of 700 million years, still quite large. Radon-222, that product of the uranium decay that seeps into your basement, 3.8 days. Iodine-131, you probably heard a lot about that in connection with nuclear accidents, particularly at Fukushima. That's a iodine isotope, and so it collects in your thyroid gland. It causes thyroid cancer. It's abundant in products of nuclear fission, so it's abundant at nuclear accidents and has a half-life of 8 days. Carbon-14, about 5,700 years. It's formed in the atmosphere by cosmic rays, and as we'll see in a moment, it's used in radiocarbon dating. And a few others here. Plutonium-239, hydrogen-3 tritium at 12 years. Cesium-137, another important isotope in nuclear accidents. With its 30-year lifetime, it takes a long time to go away, and land contamination around Fukushima and Chernobyl is due in large part to cesium-137, oxygen-15 I mentioned, used in PET scans. Potassium-40 is a long-lived isotope, 1.25 billion years, and it's naturally occurring, and there's a lot of it in your body. Eat bananas, they got lots of potassium. You're slightly radioactive from potassium. It's a significant source of radiation to you. So those are some half-lives. Well, let's see if we understand half-lives by doing another calculation here on our monitor. So I'm going to talk about radiocarbon dating, the process of using radioisotopes to date ancient objects. In particular, archaeologists like carbon-14, which is formed, as I say, in the atmosphere by cosmic rays, taken up by plants and then by animals, which plants take carbon out of the atmosphere. And this particular sample has 9.5% the carbon of contemporary bone. How old is this bone? We can give a quick answer because 9.5% is less than 1/8. 1/8 would be 12.5%, about 1 over 2 to the cubed power, 2 to the 3 power. That's 1/8. But it's more than a 16th, which is 1 over 2 to the 4th, and that's enough to tell us the age is between 3 and 4 half-lives. The half-life is about 5,700 years, so go figure it's somewhere up near 20,000 years, but not quite. That's a quick answer. A better answer comes from our formula. N is the initial number times 2 to the minus t over t to the 1/2. So the ratio n to the original number, which we're told is 0.095, 9.5%, is 2 to the minus t over that half-life, t 1/2. How do we deal with that? We take the logarithm of both sides. Logarithm of 0.095 is the logarithm of 2 to the minus t over t 1/2. And there's an identity you learned back in high school when you worked with logarithms, and it says the logarithm of something to the nth power is n times the logarithm of the thing itself. So here I have 2 to some power, so I can rewrite this as logarithm, this is the natural logarithm, of 0.095 is simply that exponent with the minus sign times the log of 2. And let's calculate it. T is t 1/2, log 0.095 over log 2. Work that out. The half-life is 5,730 years. There's the ratio, 19,430 years, as we guessed approximately with our quick thing. That's radiocarbon dating. That is a very powerful technique, and it works up to about 50,000 years out. There are some subtleties with it. We can incidentally use uranium and potassium isotopes to date things back billions of years, and that's what we do. That's what geologists use, for example, to date rocks. Well, I've talked a lot here about radioactivity. There are a lot of uses for radioactivity. Dating, as I just mentioned, isotope ratios tell us about, or isotopes and the decay of them tells us about the ages of things. Medical diagnostics, all kinds of medical diagnostic procedures, some of which I've alluded to, use radioactivity. Medical treatment uses radioactivity, particularly to kill cancer. We use radioactive tracers to see where things are going. You're building a better car engine and you want to know how it wears. You incorporate some radioactive material into the bearings and then you watch where that radioactive material goes because it's easy to detect. Some so-called activation analysis makes ordinary materials briefly radioactive, and by detecting the signature of the radiation, you can tell what kind of materials there are. Activation analysis is used, among other things, in some high-tech security scanners at airports to look for explosives. Insect control, you can use radiation to sterilize insects, and you can wipe out whole populations when they mate with sterile insects. Food preservation, a number of food products are preserved by radiation, which kills bacteria. Fire safety, smoke alarms, non-electric exit signs use radioactive materials. Radioactivity is with us everywhere and doing a lot of useful things for us, as well as a lot of harmful things. To talk about those harmful things, we've got to figure out a little bit how to measure radioactivity. The SI unit of radioactivity is called the becquerel, after Becquerel, who discovered radioactivity, BQ. And a becquerel is simply a unit of the rate at which radioactive material is decaying. 1 becquerel means you've got a bunch of stuff in which 1 decay is happening every second. An older unit is the curie, which you may have heard of. A curie is roughly the radioactivity of a gram of radium-226. It's about 3.7 times 10 to the 10 decays per second. You probably heard about becquerels in connection with nuclear accidents. They're simply a measure of how much activity there is. More significant is the radiation dose. A gray is a unit of radiation dose. 1 gray means a material exposed to radiation has absorbed 1 joule of energy from the radiation. The older unit, the rad, comparable to a gray, but equal to a hundredth of a gray. But what you probably have heard of is the sievert, abbreviation SV, or symbol SV. That's the measure of biological radiation dose. It means the same thing as the gray. 1 sievert is 1 joule per kilogram, but it's been adjusted for biological effectiveness of different kinds of radiation. An older unit is the rem, which is 0.01 sieverts. So those are units you've heard about. During the Fukushima accident, for example, there were reports on how many sieverts per hour there were at this distance from the nuclear plant, inside the reactor building, how many sieverts or millisieverts or whatever were they getting, and what happened to the guys who stepped in highly radioactive water. They got a few sieverts of radiation. So we can try to figure out what the effects are of these biological doses. The lethal dose for biological radiation, and this is a statistical thing, it's called the LD50, half of people exposed to 4 sieverts, a short dose of 4 sieverts, die. So a few sieverts is lethal. Your lifetime cancer risk goes up by about 1 part in 1,000, 0.1%, if you get exposed to 10 to the minus 2 sieverts. That's 10 millisieverts. That's not a big increase because your lifetime cancer risk from all causes is 42%. 42% of us are going to die of cancer. And so it's very, very hard to say a given cancer was caused by radiation, especially low radiation doses. You fly from New York to Hong Kong, you get exposed to cosmic rays, you get about 10 to the minus 4 sieverts, about 1/10 of a millisievert. Do that, 100 times, and you've got your cancer risk up by 1 part in 1,000. Chest X-ray is about the same, 10 to the minus 4 sieverts. If you were a neighbor of the 3 Mile Island accident and you stayed put, you would pick up an extra dose of about 10 to the minus 5 sieverts, about 0.01 millisieverts. At the Fukushima plant boundary, during the height of that nuclear accident, the radiation dose was about 1.9 millisieverts per hour. So that's how much you'd pick up if you stood at the boundary of the plant. If you went inside, it would have gotten worse. U.S. annual average radiation dose amounts to about 3.6 millisieverts, and that comes from a lot of sources. About half of it comes from radon in buildings, this gas that's naturally there from the decay of natural uranium. Rocks and soils contribute another about 8%, cosmic rays about 8%, radiation from inside your own body, mostly radioactive potassium, about 11%. Those are all natural sources. Medical procedures contribute about 15% of our radiation dose. Consumer products like smoke alarms and other things, about 3%. And finally, a little category that says other is less than 1%. That other category, by the way, includes the normal operation of nuclear power plants and nuclear weapons testing. So that's actually a rather insignificant source of the radiation we receive, about 3/4 of which is natural, and most of the rest comes from medical procedures. So those are radiation doses. Well, let's wrap this one up. Neutrons and protons, they make up the atomic nucleus. They're held together by the strong force, the nuclear force, and opposes the electric force, which is trying to tear them apart. Nuclei are characterized by their atomic number Z, the number of protons, their mass number A, the total number of nucleons. So there's helium-4, 2 protons, 2 nucleons, with its little symbol 2He4. The chart of the nuclides shows us that their number of neutrons and equal to the mass number minus the number of protons is on the order of Z, the number of protons for small nuclei, and it gets greater than Z for larger nuclei. And there's the chart of the nuclides, which we'll return to in the next lecture. Unstable nuclei undergo radioactive decay. Alpha, beta, and gamma were the 3 modes of decays we considered. A typical decay is that alpha decay. The half-life characterizes the amount of time a radioactive nucleus hangs around, and those half-lives vary from tiny fractions of seconds to billions of years. There's the half-life decay curve. And we looked at radiation, we looked at its uses, we looked at its measures, and we looked at biological doses. So there's a summary. And I want to leave you with a challenge on this one, a very significant challenge because it's one that has real implications for human health. Here's the challenge. After the Fukushima accident in 2011 in Japan, caused by an earthquake and a tsunami that wiped out the cooling systems of the nuclear reactors at one power plant, where there were 6 reactors, by the way, the levels of iodine-131, that isotope with a half-life of 8.04 days in milk samples, rose to 17 times Japan's safety standards. How long would you have to hold that contaminated milk until it was considered safe to drink? Would that be a practical thing to do? So let's solve that problem. There's the problem. Now, the activity of a radioactive sample, I haven't really talked about how that decays, but that depends on the number of nuclei. So that half-life equation applies to activity as well as to number of nuclei. So we want to know when the radioactivity is going to have decayed by to 1/17 of its original level. Well, that's exactly the same problem we had when we did the radiocarbon dating. There we were worried about a very different problem, about the decay of radioactive carbon-14, but it's exactly the same math. N is n naught 2 to the minus t over t1/2. That gives us, in this case, n over n naught. We want to be down to 1/17 of where we were. That's 0.0588. The rest of the math follows. We take the logarithm of both sides, we solve for t, and we get 33 days. About 4 half-lives, because 4 half-lives would take you down to 1/16. We want to go down to 1/17, so not surprisingly, we're at a little bit more than 4 half-lives. Half-life of about 8 days, 4 half-lives is 32 days. You can't hold milk that long, fresh milk anyway, so you'd have to dump that milk. So the answer to that question is nope, the milk would not be safe to drink before it spoiled.